Okay, so let's look at another example. This time it says, suppose the position of an object moving in a straight line is given by s of t, which is equal to t squared plus 5t plus 2. Find the instantaneous velocity. And so this example here, if we're given a position of a function, if we want to find the velocity, in this case, the instantaneous rate of velocity, we want to find that change in the speed. Is what that's asking. And so we're going to do the same way that we were doing before. We want to look at, because it's instantaneous, we're looking at the limit as h is approaching 0. In this case, it's not f of x. So I'm going to look at s of 1 plus h minus s of 1 all over h. So just in general, as h goes to 0, f of x plus h, oops, yours was a plus h minus f of a all over h. In our case, our a value, this is what we're trying to find the instantaneous rate of change at, that is at a is equal to 1. That's why I put that in here. Okay, so if you want to, you can do it in pieces. And so let's look at s of 1 plus h. So if we plug in 1 plus h wherever we see a t in our function s of t. So this would equal, I see a t quantity squared, so let's put parentheses quantity squared plus 5 times t, so let's put parentheses there, plus 2. Let's go in here and let's plug in 1 plus h wherever we have that parentheses. So we can simplify this by expanding. And so 1 plus h times 1 plus h. We need to distribute that out. We can distribute our 5 into the second parentheses. So we have plus 5 times 1 is 5, plus 5 times h, so 5h, and then plus this 2. So distributing 1 times 1, we get 1. 1 times h, so plus h. Now distribute our h, so h times 1, so plus h. H times h, so plus h squared. And notice I have some like terms right here. Well, let's just bring it down. So plus 5 plus 5h plus 2. Now let's combine our like terms. So I only have 1h squared. Let's bring that down. And now looking at all the terms that have just a single h. So you have a 1h plus 1h plus 5h. So that's plus a 7h. And then we have here constants, 1 plus 5 plus 2. So that gives me plus 8. So this was just the s of 1 plus h piece. And now we want to look at s of 1, or negative of s of 1. So if I look at s of 1, let's forget about the negative for a second. So we're going in and we're plugging in a 1 wherever we see a t and s of t. So if we do that, this is equal to, I see a t there. So I'm going to put parentheses squared plus 5. I see a t, so parentheses plus 2. Plugging in 1 where I have the parentheses, and then simplify. So 1 squared is 1, plus 5 times 1 is 5, plus 2. So this is 8. So if we plug this in to our limit, we have the limit as h approaches 0 of the s of 1 plus h, which we found to be h squared plus 7h plus 8 minus s of 1. So our s of 1 value we found to be was 8. So minus 8. And now put the whole thing over h. So notice in our numerator, those constants cancel out, 8 minus 8. So we have the limit as h approaches 0 of h squared plus 7h all over h. We need to factor out that h in the numerator so we can cancel it with the h in the denominator. So if we pull out the h from both of those terms in the numerator, we have h times the quantity h plus 7 all over h. So now we can cancel out the h's. And we're looking at the limit as h goes to 0 of h plus 7. So now if we do direct substitution, it's not going to give us that indeterminate form, and it's equal to 7. So the instantaneous rate of change or instantaneous velocity at t equals 1 is 7. Okay, so how we've been doing it, it's been looking at a particular value. Sometimes it's helpful to look at it that we look at the instantaneous rate of change of the function at any value of x, or in this case t, and then go in and plug in the numbers that we're trying to find the instantaneous rate of change of. So maybe let's look at another example where we do that first. So if we want to find the instantaneous rate of change of f of x, this is where we're going to look at the limit as h approaches 0. I didn't give us any particular x value that we wanted that instantaneous rate of change. So instead of putting a here, I'm just going to leave it with x. So x plus h minus f of x all over h. So for example, let's say it wanted us to find the instantaneous rate of change of the function f of x equals x squared plus 2. So pretty much doing exactly what we were just doing. This time we're not plugging in that number for x. And so, and you really don't have to do these in pieces. I just kind of wanted to break it down for us at first. So we would look at the limit here as h goes to 0 of this f of x plus h. So we're going to go in wherever we see a parentheses or x, we're going to put parentheses. So we're going to do a parentheses squared and then a plus 2. And we're plugging in for f of x plus h. We're going to plug in that x plus h inside that parentheses. So first piece in the numerator is x plus h quantity squared plus 2. Then we have minus, putting a minus here, of our function f of x. Well, this is what f of x is. So let's put parentheses when we plug in what our equation is, f of x. So it's minus our equation f of x, which is parentheses x squared plus 2. Then it tells us to put this whole thing over h. So we want to expand, distribute, combine like terms, factor, and then take the limit. So if we distribute it out, x plus h times x plus h, you have that plus 2. Let's distribute our negative signs. This is why it's important you put parentheses around that whole function f of x, because that minus has to be distributed to every term in f of x. So this is going to be minus x squared minus 2 all over h. So if we had distributed x plus h times x plus h, you get back x squared. The two middle terms, well, we would have an xh plus an xh. So if it's okay, I'm going to just write plus 2xh plus h times h squared. So that's distributing x plus h times x plus h and combining like terms. Let's bring down the plus 2 minus the x squared and then the minus the 2 and put it all over h. So we can start combining like terms. Well, I notice I have a positive x squared and a negative x squared up there. So my x squared terms cancel. I have a positive 2 minus 2. Those cancel. So really all we're left with is this 2xh plus h squared in the numerator. So notice in the numerator with what's left, we can factor out an h. So if we pull out an h from these two terms that are left, we're left with the 2x plus, pulling an h out of h squared, we're left with a single h all over this h. So cancel like factors in the numerator denominator. And so we get the limit as h approaches 0 of 2x plus h. So let's do direct substitution. Go in wherever you see an h. We're going to plug in 0. So that would give us 2x plus 0, which is 2x. So this is the instantaneous rate of change of the function f of x. And now if we wanted to find the instantaneous rate of change at 0. Well, if you did that and you plugged in 0, wherever you see an x here, we would have, and maybe we can call that instantaneous rate of change g of x for now. I'll give you notation. So if I look at g of 0, it's telling me that slope when x equals 0 would be 0. Or if it says find the instantaneous rate of change when x is 2. Then all we would do in here is go back in and look at g of 2. So that would give us 2 times 2, which is 4. So I know that my slope is increasing when x equals 2, a rate of change of 4. So if we went and we looked at the graph of our original function, x squared plus 2, I actually know what that looks like. That's just a parabola of x squared shifting up 2. So my vertex is at 0, 2. Have something that looks like this. And so notice at x equals 0, right here, this is where it's changing direction. And that slope there is actually 0. Which we found up here. If you look at to the right of that vertex, notice it's an increasing function. And so when x is 2, this slope right here is telling me it was a slope of 4. Notice if we plug in a negative number, so notice this function is decreasing to the left of x equals 0. And so if we plug in a negative number, we better get back that that slope is negative. Notice if we choose a number bigger than 2, right? If I plug in a number bigger than 2, notice that slope there. It's still increasing, but notice that that slope here in this case is a lot larger than this slope here. So let's try it. If I plug in x equals 5, I should get a steeper or a bigger number, which means that slope is larger and it's steeper. So if I looked at g of 5, this would be 2 times 5, which is 10. So if you had calculus before, or basically just took the derivative, and this is what the next section is, we just took the derivative of our function f of x, and the derivative basically gives us where we can find what the slope is at any particular value on the function. So far in our mathematical careers, the only time we were able to find slopes was when we had a line. And then the slope was always the same any 2 points you chose on that line. But now we can extend this and find the slope on any curve, if it exists, by looking at the instantaneous rate of change.